In this video, I'll talk about how we implement the ILP model of the learning curve problem in Excel to solve it. First, let's review the decision variables we defined for this problem. We have two groups of decision variables. The first group represents the number of equals bus to produce, represented as x11 and x12. And the second group represents the number of hydrolysis that we're going to produce. Within each group, we have two decision variables. One represents the number of the equals bus produced within the first 75 units, and the other represents after the 75 units. Same for the hydrolysis. The first represents the number produced within the first 50 units, and the second one represents number produced after the first 50 units. So we'll keep this in mind when we implement it in Excel. Let's open the data file and copy those basic information to a new sheet. Now we have the hydrolysis, the 2-unit profit here, and the equals bus and hydrolysis here. And we're going to move this a little bit. And we'll put number to produce. Number to produce. So we'll highlight these 4 cells to represent our 4 decision variables that correspond to the 4 different unit profit we'll have. So for example, this one highlighted here represents the number of equals bus to produce within the first 75 units. That corresponds to a unit profit of 350. And this one represents the number of equals bus to produce after the first 75 units. And each of them will have a unit profit of 375. We'll put the total profit here. The total profit equals to just the sum product of those unit cost and the number to produce. Okay. So we put the decision variables in this way, in the same format as the unit profit. So when we take the sum product, it will just take the 350 times this one plus 375 plus this one plus 300 plus this one plus 325 times this one. We'll highlight our objective function in blue. Okay, so with this, we take care of the decision variables and the objective function. We can take a look. Objective function is the unit profit and those decision variables. Take the sum product of them. Okay, now let's look at the first group of constraints. First group of constraints represent the resources used need to be less than or equal to resources available. And note that the coefficient of x11 and x12 are the same here, same here, and the same here. Okay, because they both represent the number of equals bus to produce, and the unit of pump, labor, and the tubing used for equals bus, they are the same. Same as like the second part. Those ones, the x21 and x22, they both represent number of hydrolysis to produce, and the unit of pumps, labors, and tubing the hydrolysis used, they should be the same. So let's look at the first group of constraint. So for the first group of constraint, to make it, so basically we want, let me insert one. So those are, we want like resources used less than resource available, right? So resource, or say need. And for this part, basically we want equals bus, sorry, equals bus multiply pumps used plus this multiply. This is also the equals bus, right? Multiply this again plus the hydrolysis times the hydrolysis pump needed would be this value here. But we don't want to just like type like this. We want to make the formula copyfiable later. So let's think about how we do that. So we're going to use this value. This is equals bus produced, and this is also equals bus produced. Can we? If we look at this row, these two both represent the equals bus number, and the next row represent the hydrolysis number. So if we want to just take the sum product, like the similar format as what we did earlier, we would want this row to represent the equals bus, and then the next row represent the hydrolysis. So what I'm going to do is to just move this value here, and here this value should equal to this one here. Okay, and the same, this equals to here. So in this way, what I put is that these are both the pumps needed for the equals bus. So this would be a little misleading now. I'm going to just take away those. And I'm going to move this down too. And move this 6 here. So we need a 9 and a 6. Okay. Oh, move this back. And then this 6 should come here. And okay, so with this arrangement, let me just do some, make them the same. With this arrangement, I can take the sum product of these four cells with these 4 cells and to calculate the value here. So sum product of these ones and these ones, to represent the left-hand side of my constraint here. So it's the 1 times x1 1 plus 1 x1 1 2 plus 1 times x2 1 plus 1 multiply x2 2. So 4 decision variables with 4 coefficients, add them together. These are the left-hand side. So that will be the same to the next 2 constraints here. And later, I want to copy this formula down to calculate the labor and the tubing needed. But I don't want my decision variables array to move. So I'm going to fix them. I'll just fix the row number. So the row number here, I'll put the $sign. But I do want the coefficient to move accordingly. So just Control C, Control V, Control V, and click this inside to check. Okay, so it's the sum product of these 4 cells with these 4 cells to represent the third constraint here. Okay, and I want to change the color here. I don't want to shade those ones. Okay, so those will be my left-hand side, right-hand side, left-hand side, right-hand side. Okay, so those are the first group of constraints. You can have different designs. For example, if you want to say move the high cost bus and the hydrolysis to just one row, and here instead of like 2 row and 2 columns, you can have 1 row, 4 columns. Then here would be the same format. Okay, so we can give it a try. For example, if you move these two here, and then you would move these here, and then or move those values here. And this way may be easier later to do when you define the constraint table. For example, like this. Okay, then we'll have to change the formulas inside. The formulas will instead of be the sum product of those ones, like this, and then copy. Okay, so we keep changing. So we'll copy this way now. Click inside to check. Okay, so it would be like these 4 multiply these 4. So whichever way you found it easier for you. You see, when we move to this way, what we want to do is to just move the number to produce to be like to here. So those represent number to produce, and then the first 2 will represent the hydrolysis. So if I just merge these here, and then these ones merge, yeah, and then we'll have these all represent the number to produce, and but these first 2 are equals bus, and these 2 are hydrolysis. Okay, so I think this way may be easier for us to input the constraints later. So we'll just continue with this one. Okay. Next, we need to, since we decide to move the format like this, we'll have to update the formula in the total profit window too. So we're going to change it to be the sum product of this row and this row here, so the 2 rows. And once we do this, you may find some of those headings can be improved too. For example, I'm going to delete this one and just use this row to represent. That's the unit profit. Okay, and change the format here. I don't want them to merge. I only need 1 cell here. Okay, and those heading can go above now. Those extra spaces, I also can just delete them. So here this would be okay. You need to produce, and that's the total profit. Okay. Now let's look at the additional constraints we have. We'll use this model. So that's the complete model. And though in the lecture we talk about we don't really need this right-hand side for this constraint. So like the 75 here, the 50 here, we don't really need them. We need because according to what the problem will be solved, the x11 will never go to 75, so we don't, and the same as x21, they won't go to 50, so we don't need the upper bound for them. But those are the constraint, like the complete constraint that we came up with, that logical statements. We'll implement them. Okay, now let's look at to add those linking constraints, we need to have the y's. We have a y1 here to link the x11 and the x12 together. And we also need that y2 to link the x21 and the x22 together. So in another word, we need a binary variable for each type of the hot tub. Okay, so we need a y1 and a y2. Where should we put them then? So I would call those, so I'm going to add just like a linking constraint. Linking. So those represent like those resources constraint, the basic ones, but now we're going to add the linking constraint. The linking constraint. And the first one, we have the y1. I'll just label it here. Y1 and Y2. Since Y1 corresponds to the aqueous bus and the Y2 corresponds to the hydrolysis, I'm going to move Y2 here. Then we'll look at that linking constraint. So the first one is that for the first decision variable in the aqueous bus group. So aqueous bus need to be greater than or equal to the 75 multiply this Y1. And if we look at the 75, we can interpret it this way. This is the minimum volume that the production of aqueous bus has to reach before the company can reach the next level of the higher profit. Okay, so this 75 is the minimum volume. I'll put the minimum value here. So the minimum value is this 75. And for the hydrolysis, it is the 50. So the production of hydrolysis have to reach 50 in order to increase the profit to the next level. And we're going to just highlight these two cells here to represent these are our Y's. Okay, now then the minimum multiply our Y will be equals to this multiply this. Copy here. So this one represents the Y2 multiply the 50. And these will be the, say, the left-hand side or right-hand side. And the other side will be the x11, x21. Just to make it easier to implement in solver window later, I'm going to put the x11. Okay, so x11, this equals to our x11 value. So you just refer to this decision variable here. Same. x21 equals to this value here. You just need to be very careful that you refer to the right cell. Okay, this one is the x11 value here, and this one is the x21 value. It's this one here. And we'll just highlight them. One as the left-hand side and the other one as the right-hand side. So in this case, it really doesn't matter. So this is the left-hand side. And this is the right-hand side. Now the next we're going to implement these two. So for this two, it's the different x. It's the x12. Okay, and need to be less than or equal to the big M times the y. We'll put the big M. And here is the M multiply y. Now for this big M value, we talk about it being the upper bound of our x. And in this particular problem, the x12 represents the amount of aqueous bus that you produce starting from the 76 units. So you will need to find out in total what's the maximum amount of aqueous bus you can produce, subtract the 75. That will be the upper bound of your x12. So we'll first find out what's the maximum amount of aqueous bus that we can produce if we use all the resources just to produce the aqueous bus. Nothing with hydrolysis. Okay, so it's the same way that we find out the big M in the fixed charge problem. So will be the minimum value among this allowable resources divided by the unit of pump needed, the available labor divided by the labor unit needed, and the available tubing divided by the tubing unit needed. We'll take the minimum among those three, and here we're going to subtract this minimum value, the 75 here. Sorry, there's a typo here. Divide. Okay, so 99. And the same for the hydrolysis. We're going to find out the upper bound of our X22. And X22 is the amount of hydrolysis that we can produce starting from the 51st unit. So we'll find out what's the maximum amount of hydrolysis that we can produce, assuming we only produce hydrolysis, and subtract the 50. So we'll use all the resources to produce hydrolysis. So this resources divided by 1 here. This one divided by here. And this divided by this. And subtract the 50. Okay, so we find the big M for our X12 and our X22. Now the Y times big M will be this. Okay, so the Y times the big M. Same here. It's the Y2 times the big M. And the X12 again referred to here. Okay, so X12 is this value, and X22 is this value. Make sure you refer to the right one. And you know, when you implement the model, if you found it easier for you to remember or just clear, you can feel free to put like X11 here, X12, and this is X21, and this is X22. Just to help yourself to make it clear, so you don't refer to the wrong volume, the wrong cell. Okay, and later you can delete them. Now this will be again my one of my left hand side, and this will be another left hand side, and those two will be my right hand side. Left hand side. Okay. Now we have for all the linking constraints implemented. Then we're ready to go to the solver window. Okay, now so we go to the solver, and so our objective function is this total profit, and we want to maximize it. The decision variables, we want to highlight our X. Okay, and don't forget the 2 Y's. Okay, so you see all those 3 appearing here, and we'll add the constraints. So the first group of constraints will be resources needed less than equal to resource available. So this is one group. And then we'll have to add those linking constraints. So for the linking constraints, since we already put like the minimum and the big here, so it will be easier to help us remember which direction our sign should be. Okay, so we'll put the first one. The first one is the X11 greater than equal to, because it's a minimum. Okay, so it's greater than equal to the minimum times the Y. And same here. So X12 greater than equal to this minimum Y, minimum times Y. Okay. And the next one would be the X12. Now it's less than equal to the big M now, because big M is the upper bound of your X. So less than equal to the big M times the Y. And this one less than equal to the big M times the Y. Okay, and make sure you add the integer constraint. So the number to produce need to be integers. And the y's need to be binaries. Okay, now we're going to change the algorithm to LP simplex, and make sure you look at the option part. This integer optimality is 0%, meaning that we are going to find the true optimal. Okay, click solve. Okay, so the solver find the solution, all constraints and optimality conditions are satisfied. So that means we did find the true optimal solution. And we'll click OK. But whenever you get the result, make sure you check the solutions to see if it makes sense. Okay, in this specific problem, we want to make sure that the condition that we used those constraints to enforce need to be met. For example, here we do have x11 being 75 when our x12 is greater than 0. So and the same here, our x22 is greater than 0, our x21 is 50. So in total, we are going to produce this plus this one, 122 equals bus. Okay, and we are going to produce 78 units of hydrolysis, and this is our total profit. And if you want to do some just like a cosmetic work to make it make the number, the format, everything look better, then feel free to do so. But this is the solution. So we are going to make 122 equals bus and 78 hydrolysis. This is the total profit. And those different levels of profits are achieved by the different numbers that produced here.